Alright, so in this video here we're going to talk about inverse variation. Right now, if you haven't seen the video that I did on direct variation, you might want to check that one out. And I'll do another one also on what we call joint variation. There's several different types of variations. Right, what we saw in that video on direct variation is that in direct variation, as one variable increases, the other one also increases. Right, if one of them decreases, the other one also decreases. So they're directly proportional to each other. Right, they either both go up or they both go down. In inverse variation, it's an inverse relationship. So in inverse variation, as one variable gets bigger, the other one actually gets smaller. Right? As this one gets bigger, the other one gets smaller. Right? So they're going in opposite directions when you have inverse variation, whereas in direct variation, they either both go up or they both go down. All right? So inverse variation is represented by this formula, y equals k divided by x. All right, so remember, direct variation is y equals k times x. Now we have y equals k divided by x for for inverse variation. And also here, the k cannot equal 0. Right, k can be any other real number besides 0. All right, and k once again is what we call the constant of proportionality. All right, now a couple of the key words that you'll see when you're doing these word problems that involve inverse variation. It'll say y is inversely proportional to x, or y varies inversely with x. So those are the key words that you look for to let you know that you have inverse variation as opposed to direct or joint variation or one of the other types. Right, so the word inversely is there, so it should be pretty clear when you have inverse variation. You just have to read the problem carefully and pick out that word inverse in there somewhere, and then you know what you've got. All right. So here's what the graph of inverse variation looks like. If you remember, direct variation was just a straight line. It was like a linear equation. Inverse variation is not a straight line. Right? And like I said, it has that inverse relationship. So as x is getting bigger as you move off to the right, y is actually getting smaller. It's going down. Right? As x gets smaller as you move to the left, y is actually getting bigger. Right? So as one variable goes up, the other one goes down, and vice versa. Right? So that's the nature of inverse variation. All right, so that's just a little bit about what inverse variation looks like. I'm going to pause the recording, erase all these notes, and then put up an example where we'll work through a problem and solve a problem that involves inverse variation. Alright, so I got an example up here. We have the frequency of a vibrating string varies inversely as its length. A string 3 feet long vibrates 175 cycles per second. Find the frequency of a 5-foot string. Alright, so if you watch the video that I did on direct variation, this problem is kind of set up the same way, and the method that we'll use to solve it is pretty similar to that one as well. It's just that we have a different type of variation here as opposed to that last problem. Alright, so here, the frequency of a vibrating string varies inversely. So first key thing when you're doing one of these variation problems, identify the type of variation you have. Is it direct variation, inverse variation, joint variation? This one says varies inversely. That tells us that our equation is going to be this inverse variation, y equals k divided by x, so we know how to set up our equation. Right? Next thing, I want to actually set up that equation. So I'm going to use letters that represent the things that I'm talking about. So we're talking about the frequency of a vibrating spring. So let me call that F. Right? So it's going to be F is equal to k divided by, it varies inversely as its length. So let me use the letter L to represent the length of the string. Right? I don't know if you can see that L very well there, but hopefully I wrote it a little bit better down here. Right? So I have F equals k divided by L. Right? You can use y equals k divided by x, but when I have to start plugging numbers in here for the frequency and the length, if I have to plug in 3 feet for the length of the string, well, if I have y equals k over x, is x the length or is y the length? I'm not quite sure which one is which. Whereas 3 feet long, I use L for length. I know that the 3 feet goes for L because that's the length of the string, right? So, like I mentioned in that other video on direct variation, it's a real good idea to use variables here instead of just x and y every time. It's a real good idea to use variables that represent what you're talking about. In this case, f for frequency, L for length. Then when we have to plug the numbers in, we know exactly where the numbers go, and there's no confusion. The biggest mistake I've seen people make in the past on a problem like this is to do exactly that. Right? To say, oh, 3 feet, that's the length, let me plug that for y. But actually the length is supposed to go down here, where when I call it L, it's easier for me to identify that. All right, so anyway, I set up my equation, F is equal to K over L. I know it's going to be like that because it says varies inversely, right? The inverse variation is that fraction relationship, that dividing relationship. right? So the frequency varies inversely as its length, f equals k divided by L. Right, the next thing that I need to do is find k. Right, once I set up my equation, identify what type of variation I have, get my equation set up, I need to find the k value. I need to find that constant of proportionality. And in order to do that, they have to give me some numbers for the frequency and the length, for the f and the L. And they do that right here. A string 3 feet long vibrates 175 cycles per second. Right, so the frequency is the 175 cycles per second, so 175 equals k divided by the length of the string, which is 3 feet. So 175 equals k divided by 3. Right, in order to solve for k, you have to be given in the problem some full set of information. Right, if we're talking about frequency and length, they need to give us a frequency and a length that go together. Right, when the string is this long, this is the frequency. You can plug those numbers in for f and L like we did here, and now you're able to solve for k. Right? Remember, with these variation problems, you can't just say, oh, find the frequencies of a 5-foot string, let me just plug that number into the equation and I get my answer. Right? It's always going to be this two-step process. First you plug in the numbers they give you to find the constant k, and then you set up the equation and you plug in the other number of what you're actually trying to find in this problem. Right? It's always going to be that two-step thing. Right? So if 175 equals k divided by 3, to solve for k, I need to multiply both sides of this equation by 3. Right? K divided by 3, the opposite of dividing by 3 is multiplying by 3, and 175 times 3 is 525, I believe. It is 525, yes. Right? So k equals 525. Right? So that is my constant for this particular problem. Right? My k value is 525. Right, so what I do with that now is I take that k value and put it back into this equation, right, which is going to give me f equals 525 divided by L. Right, the frequency equals my constant 525 divided by the length of the string that's vibrating. Right, so now that is the formula that I need to use now to actually answer the question, which they ask us to find the frequency of a 5-foot string. Right, so I'm looking for the frequency, I'm looking for f, they give me the length of the string, and again, because I chose letters that were appropriate for the variables and for the real life situation here, it's pretty easy to figure out that 5-foot string, I put that number 5 for the length, and I'm trying to solve for f, which is the frequency. Right, again, that's the advantage of not just using x and y every time. I can't stress that enough because I've seen a lot of people in the past make those types of mistakes. Alright, so now that I've got my k and I have my equation set up, I have f equals 525 divided by the length of this string, which is 5 feet. So now I'm just going to have to do 525 divided by 5. So my frequency is going to be 105 cycles per second. All right, that will be the frequency of a string that is 5 feet long. All right, so that's an example of using inverse variation. Again, when you're reading one of these variation word problems, first thing you have to do is identify the type of variation. Is it direct? Is it inverse? Is it joint variation? This one says it varies inversely. That tells me what my equation is going to look like. I write that equation putting in proper letters for the variables I have, the frequency and the length. I plug in the numbers they give me for frequency and length in order to solve for k. Right, so I plug in whatever it was, 175 for frequency, I plug in 3 for the length, I solve for k, I put that back into this general equation here, that gives me the formula I need, and then I plug in the last number that they give me for either L or F, depending on which one they give me, and I solve for the one that I'm trying to solve for. That's how you approach pretty much all of these variation type problems. The key thing is identifying the type of variation, and then also knowing the different types of formulas, knowing that direct variation is y equals k times x, but inverse variation is y equals k divided by x. Right? If you can get those formulas down, the method for solving these problems is always the same no matter what type of variation you actually have. All right, so I'm going to do another video now on joint variation, which is another type of variation with a slightly different formula from these other ones. All right, so make sure you check that one out as well.